standard mode corresponds to this actually. And this is we change the number of the dark fermion, and then it changes. But in terms of theta, this every point fall on this universal curve. And this is also true for Z prime boson mass. It depends on the theta h. And how about Z prime? So this is Z prime. In this scenario, there are three bosons. First KK boson, KK side state of Z boson and photon, and also there is one more ZR, corresponds to the SU2R, and these constitute Z prime. And this theta h, if theta h is 0.114, this is the production rate at 14 TBLSC. And so you see that you should see some excess here. If theta h is smaller, then this Z prime must become bigger, and it will become cross section becomes a little smaller. So this is the value, and this width is relatively big. This is because it turns out right-handed covalent reactant coupled to this KK blue, KK gauge boson relatively strongly. 3-4 times bigger than the normal coupling, and that gives the larger width. How about W prime? We checked this one recently, and for instance, for Z prime, for the Z prime to lepton pair, or one more channel is Z prime to ZA, and this is the product rate. And for W prime to TB, it is a little bit bigger, but the W prime to leptons is much smaller, and it's hard to see actually. And also W prime WH is so these formals, particularly this Z prime to electron positron or mu plus mu minus, this we should explain. And I think if you get 150 per inverse data, then you should see 20-30 excess. Okay. Then, so it's quite promising. Then we think, what's next? Well, beyond LSC, and I would like to argue that we should examine the gauge Higgs grounding. Of course, we have strong interactions. So if this is right, then you have to incorporate strong interaction as well. How do you do it? So let me first present in the 5-dimensional. In 5 dimensions, we should look for this SO11. We concluded that the only good gauge group is SO11. And we consider in the Landau-Sandra space. But now we have two orbifold boundary conditions. In the electroweak cell, we take the same one. But now you can take two different things. On this one, UV plane, P0 is I10 and minus 1. So SO11 breaks down to SO10. On the K plane, IR plane, this is I4 and minus I7. That means the SO11 breaks down to SO4 times SO7. As a whole, the symmetry breaks down to SO4 times SO6. Okay? And so gauge field, for gauge field, with this boundary condition, you have SO4 massless gauge boson and SO6. SO4 is SU2L times SU2R. SO6 is SU4, which contains SU3 carbon. For the hexadimensional component, it turns out with this boundary condition, so 0 mode appear, parity even mode appear only here. This is SO4 vector, SU12 doublet, and color single SO4 6 single. And so you get only this one. And how about quarks and leptons? These are introduced in the 32 and 11 of SO11. 32 is a spinor differentiation of SO11. And it decomposes to SO10, 16, and 16 bar. And the 16 and 16 bar contain this one. And the zero mode appears only here. And these are lepton and quarks. And left-handed zero mode appears only in the 16, and right-handed zero mode appears only in the 16 bar. So all other modes are heavy. And so it's all quarks and leptons are contained in the 32. And 11, it depends on the boundary conditions. Typically you have this kind of thing. And down contact number is contained here actually. And so you have to combine it. 32, if you have only 32, then all quarks and leptons are degenerate, and you cannot produce like quark leptons. Now, in addition to this, you have to introduce brain scaling on the 16, and then you get divided spectrum. Now, one consequence is in this scenario, proton decay does not occur. This is the grand unified cell, GAC cell. In ordinary four-dimensional GAC theory, normally you get necessarily you get but in this scenario, all quarks and leptons, okay, as you show, as I show, you can impose this psi fermion number conservation, and the proton has UUD and then psi to 3, whereas this right hand side is E plus is -1, and so it's 44. So that's one interesting thing. However, it turns out this model is exotic light particles, like exotic particle which has a charge in -2/3 and +1/3, and +1 lepton and so on. Actually, we found that this is unavoidable. And so, to cure this problem, we concluded that you have to go to the 6-dimensional. In the 5-dimensional theory, it's not very possible. And a couple of words actually. This is SO11 gauge simplification in the hybrid warp space. So you start from the 6-dimensional space. So here, why then this warp dimension? But here, instead of a 4-dimensional Minkowski space, this is 4-dimensional Minkowski times S1. And so you identify this -y - v to yv. And this becomes O4. And the resultant is this is the ADS space, and you have a brain here, 5-dimensional brain, but S1, 1-dimensional is S1, and it's so good. And so in the 6-dimensional, this is you find 4 fixed points actually, and so there appeared 4 before the boundary condition matrix, but only 3 of them are independent. And you take this P0 equal P1 equal I4 minus I7. And P2 and P3 in this direction, in the 6-dimensional space, you take I10 and minus. So this leads to the, in the 5th dimension, you get the previous KK scale, which is 6 to 10 TeV. But in the 6th dimension, you get 1/R6. This is supposed to be gap scale. And it works. And you find no exotic light particle, and we are currently trying to reproduce all quark lepton spectrum. So soon, I think I can report. Now, one comment in the 6th dimension, how do we get chiral fermions? Well, in 6 dimensions, okay, this is all before the condition actually. And if you minus y minus v are related to yv, okay, and this gamma bar is gamma 5, gamma 6. Okay. And a 4-dimensional gamma 5 is given by this answer. So if you first consider the 6-dimensional Dirac field, you have this structure 8 components. Now, in 6th dimension, you can impose the 6-dimensional wide function. And the 6-dimensional wide function is this gamma 7 in 6th dimension, which is given by this. So, say you take only upper half or lower half, plus all four conditions. Then you can find that indeed 0 mode now becomes higher. And Dirac equation is typically given by this one actually. So 4-dimensional part and the 6-dimensional part, 6-dimensional part. Plus, you can introduce this one. This is in the original Landau-Sandram. We call it the bulk scalar mass because it was scalar information. But here you have to introduce in the gamma 6 coefficient of gamma 6. So it's bulk vector. And then most of the phenomenology algebra in 5-dimensional can be applied. All right, let me summarize. So I discussed SO 5 times U1 gauge fixed electroweak unification. It's quite promising, and I think that low energy gives almost the same phenomenology as the Phelps standard model. But now you should look for the signal of this gauge fixed unification in the G prime and W prime, particularly G prime, and some Higgs strength. And I discussed SO11 gauge fixed unification. And I think so this scenario is very interesting.
Okay, very nice talk. And I have one comment and one question. This OB-fold or this extra dimension, from extra dimensions obtaining 4-dimensional chiral field and gauge group is known from string compactification. So, for example, in 1987, we obtained all standard model spectrum from string compactification. Of course, you wrote Hosotani2 before 87. Basically, this Ibanez, Quevedo, Milles, this Wilson line is your theta, basically. So we use all these, we obtained that. And after Kawamura, they did this field theory framework. So you stated this in the field theory framework. So all this mechanism was known 20 years before you cited. That's one comment. And it has all 3 families. Everything is there. Now, question is, if you have these gauge couplings in extra dimension, how do you obtain CP violation? What is the mechanism to obtain CP violation?
Okay. Second part, CP violations. But here there are I didn't describe, but there is a bulk scalar which you have to introduce, and there are couplings on the plane y equals 0 basically. Coupling between this bulk scalar and bulk fermions. In the Dirac unification scenario, you need not introduce brain fermion. It turns out brain fermion and the bulk fermion. But there are here the coupling between the bulk fermion and this brain scalar. And that one coupling, you can introduce some complex parameter. Yeah.
Usually in string compactification, this strong UFR insular organ space that gives complex parameter. So you just put in by hand?
In some sense, that part. Yeah, well, that part we haven't explored very much actually yet.
Why did you discard the possibility of using just a SU3 cross U1 and you went to SO5 cross U1? I mean, you had two possibilities. You used SO5 cross U1, but you could also just use SU3 cross U1.
Okay, that doesn't work. Okay, good point of SO5 cross U1 theory is, first of all, you can get dynamical electric symmetry. And also, normally, if you start from SU3 cross U1, you can really introduce correct Weinberg angle and this dynamic electric symmetry. Normally, what you do is you will introduce quarks and lepton in various representations, like 6 and 15 of SU6 and so on. Okay, that way you can reproduce the mass spectrum. Say you tune the 5 parameters such that you reproduce the quark lepton mass spectrum, but then you spoil the Weinberg angle and so on. And also, there are a lot of problems because in the flux space, W boson and Z boson, in the lambda Sandra, what happens is W boson, Z boson wave functions in the fifth dimension are almost constant, but it changes near the top plane. And so, phenomenology of W boson and Z boson remains almost the same as in the standard. But in the flux space, wave function is expressed in terms of sine and cosine function normally. And so if theta is not really small, like 0.1 or so, then you necessarily get some deviation in the various couples at low energy. And so you can really reproduce a standard model phenomenon. So people don't discard all those details, just focus on the spectrum as well.
Because that model without these extra dimensions works better. It's very nice and in fact becoming quite popular extension these days. Now you seem to say that the problem is with the getting the bulk factors correct to reproduce all the parameters of the mass.
Yeah, plus dynamic electric symmetry.
Plus dynamic.
So in the six-dimensional theory, when you identify the compactification scale as a gas scale, don't you automatically reintroduce the gate hierarchy problem again for the Higgs mass?
For the Higgs mass, no. There doesn't appear. So Higgs mass, okay. There appears two types of Higgs. Okay. From the fifth dimensional component of the gate potential, you get the standard model with Higgs boson. Okay. And from the sixth dimensional component, you get an additional one. But it turns out, okay, additional one is has a masses of order gas scale times gauge coupling, so it's very heavy. And for the four-dimensional Higgs, you compute effect potential still fine, even in the six-dimensional one, you can show. And so it appears in the electronics.
I mean, what is the symmetry to protect this quadratic sensitivity to the new scale? If you don't introduce supersymmetry, then what is the symmetry to prevent the Higgs mass correction?
No, okay. So there is no supersymmetry, but there is a gauge imbalance, and therefore Higgs mass. Okay. But I cannot predict, but it comes up naturally at the electroweak scale because it's related to the curvature of the effect potential, the mean. And effect potential in the flux space is dictated by KK scale. But in the random Sunderland warp space, it turns out that one time there is you get natural suppression factor from the warp to warp. And that gives naturally you get an electroweak scale. And there you don't need any fine tuning.
I mean, that's a fit. You can always fit in principle.
Yeah.
Choosing appropriately the parameters in warp space to reproduce all the masses.
Right.
So in that sense, you don't need choosing.
That's right.
For random syndrome, of course, I understand. But you have additional flat actual dimensions.
Well,
that one doesn't have this warp to help you to reduce the scale.
Yeah, that is, however, okay. So in the sixth dimension, there is S1, radius of S1 is supposed to be very large. And we want to determine that by solving the normalization group equation actually. That part is still come down.
Okay, last question, Jennifer.
Yes, so I think in the SO5 cross U1 gauge Higgs electroidentification model, you show that the Higgs coupling to the standard model particles are rescaled by the parameter cosine theta h with respect to the standard model prediction. So does that mean that if we observe the Higgs boson coupling to standard model particle, say larger than 1, in the next coming HC, then we can exclude this kind of model?
Yeah, okay. So cosine theta h, theta h to 1 to 0.1 means cosine theta very close 0.99 or so, right? So it's very hard. If say you find this deviation, say 0.1, 0.9, so then that means theta is much bigger. Okay, but that then C prime boson mass must be much lower, and which might contradict. Now we check that if theta is 0.2, okay, then already it contradicts with the current bound of the Z prime about 3 TeV. So theta h must be smaller than 0.15. And also one more thing actually I should say is theta h can't be very small. And in this model there is a lower bound, 0.07 or so. Because if the theta is below that, then you can really reproduce top of mass and that. So there is some limit.
Okay, we should move on. Let's thank Hosotani-san again. Our next speaker is Kim En Chun from